So in this talk, I would like to talk about this recent paper of mine, Obstruction Theory for Moduli Spaces of Frame Flags of Sheaves over the Projective Plane, that I wrote together with Marcos Jardim and Rodrigo von Flach. But as this is basically a natural continuation of a previous work of the other two authors of 2017, I will also give a review about this previous paper here. In fact, also the two titles are very similar, so you can understand that it's the same topic. Actually, I decided, before going into the details of the content of this recent work, to give some general ideas about quivers and representations of quivers. Just because it can be a kind of a basic stuff, but maybe it might be of some interest just to understand what a quiver is and how does this branch of, let's say, algebraic geometry, but it's more an algebraic side, works. So a quiver is just a fancy way to call a finite-oriented graph. In literature, sometimes you can also find infinite quivers, but since in my setting, never I will deal with the infinite quivers. I prefer just to put the finite condition directly in the definition. So it is just given by two finite sets that I shall denote by I and E. The set I denotes the vertices of the quiver, and the set E, that it would stand for edges in principle, but let's call them arrows actually, because the graph is oriented, is directed. Okay. Then formally, we would have two maps, S and T, from the set of arrows to the set of vertices, defining precisely which is the source and the target of each arrow. So these data formally encode something that pictorially we can see like this. So a bunch of vertices and a bunch of arrows among them. So in this very basic toy example, we have this quiver Q, which is formed by three vertices that I labeled as 1, 2, 3, and two arrows A, B, that we can so interpret as, let's say, two edges and two functions, source and target, that give for every edge the direction. So the source of the arrow A is vertex 1, and the target of arrow A is vertex 2, and so forth. There is no condition about the possibility of having multiple arrows between two vertices. It is possible to have closed paths, like this one, like this triangle, it's okay, and even just loops involving a single vertex. So this kind of picture includes all possible things that can happen in a quiver, and that they are completely okay. So we can have all of these. Perfect. So now that we understood what a quiver is, we want to fix a base field that for us will be always the complex numbers. But in general, it's okay. Of course, most of the things we are saying can be extended for a generically algebraically closed field K. A representation of a quiver is given by a collection of complex vector spaces, each one for attached to each vertex of the quiver, and a collection of linear maps between them. So linear maps phi A, sorry, going from the vector space attached to the source of the arrow A to the vector space attached to the target of the arrow A. We are always considering finite dimensional vector spaces. So the dimension of each one of these VI is always finite. And the collection of all the dimensions is called the dimension vector of the representation, and it is an element of n to the I, where I repeat, is the set of vertices of the quiver. Again, a toy example can be the following. We consider just a quiver Q made of two vertices and just one arrow between them. Then we can fix the dimensions m and n attached to the two vertices. So mn would be the dimension vector of our representation. And an example of a representation of this quiver is given, for instance, by choosing precisely the two vector spaces Cm and Cn, Cm attached to vertex 1 and Cn attached to vertex 2. And this arrow becomes simply a linear map from Cm, Cn, which can be represented by an n times n matrices with complex entries. So this collection is an m-n dimensional representation of this very simple quiver Q. Okay. What we want to do at the end of the day is to build moduli spaces of representations of a given quiver. So, roughly speaking, what we want to do is to classify representations of a given quiver, of course, with a fixed dimension vector up to isomorphism. What is a morphism between representations of a given quiver Q? This definition is kind of a categorical definition, if you want. You can really see here a diagram that would appear very often when dealing with the category theory. A morphism between so V and W, let's say, is just a collection of linear maps Fi with the index I running through all the vertices between the ith vector space Vi and Wi. And of course, this collection of maps has to be such that all the possible diagrams that we can draw, fixing edges, every possible edge of the quiver Q, have to be commutative. So from the vector space attached to the source of A and the vector space attached to the target of the arrow A, we would have the linear map phi A of the first representation. The same happens for the vector spaces of the representation W with the linear map psi A. And then we would have these horizontal linear maps, which represents precisely like the components of the morphism of representations. We want this commutation. An isomorphism is then, of course, simply a morphism where all the linear maps involved are bijectives. And in particular, two isomorphic representations share then the same dimension vector, of course. Just to give a taste of what we are doing, let's consider an apparently even simpler quiver of the previous ones. This one with just one vertex and one loop. So two different representations can be, for instance, given by choosing as vector space Cn, and then I chose the same dimension here because, of course, if not, the two representations cannot be isomorphic. And then two endomorphisms that can be represented by two matrices M1 and M2, n times m matrices. Okay. So basically, here you would have just one diagram that we can write down. So here we would have Cn in all the four vertices of the square. In vertical, we would have the two maps represented by M1 and M2. And in horizontal, we would have this sole component F1, which has to be invertible to get an isomorphism, so that basically the two matrices M2 and M1, I'm here identifying matrices and endomorphisms, of course, by using the canonical basis. So the two matrices M1 and M2 would be conjugate. In other words, this isomorphism of representations is just a change of basis, if you want, of the vector space attached to the vertex 1. So let me do now a jump and conclude in general that considering isomorphism classes is the same as modding out by the action of this huge group, which is the product of all the general linear group associated with each vector space, whose action is just given by change of basis. At each vertex, we are allowing a change of basis. Okay, so one last thing about this general quiver representations theory, that we can also represent quiver with relations. To represent a quiver with relations, that means that we just consider collections of linear maps satisfying some fixed equations. For instance, let's consider again this very simple quiver with this relation a squared equals 0. I'm writing like this because actually from another point of view, to represent a quiver is the same as representing the so-called path algebra of the quiver, but I don't want to enter in details here. So that considering quiver with relations is the same as considering representations of a quotient of this path algebra. So we would have to fix an ideal. In this case, n-dimensional representations of this quiver with this relation would be the same as considering n times n matrices, which are nilpotents of index 2. Okay, so such that a squared equals 0. Just to give an idea. Okay, so now the goal of the talk is to use quivers and moduli spaces of representations of quivers to describe moduli spaces of some geometrical objects that I am now introducing. So we are on the complex projective plane P2, and we want to classify these objects that we call framed flags of sheaves. I remember that, okay, anyway. So it's just a triple made by two torsion-free sheaves, E and F, on P2, of course, with the property that they are both trivial along the line at infinity of P2. So we are requiring that the restriction of F to L infinity is isomorphic to the trivial sheaf. This one is just the trivial sheaf, or if you want, the trivial bundle, okay? Plus, we are also fixing a specific isomorphism phi. So the objects we are considering here are, I repeat, triple EF phi. Two torsion-free sheaves, where the first one is actually a subsheaf of the previous one, with this property that they are trivial along this line at infinity. And we want also that the subsheaf respect this framing. So technically, we would say that we would require that the quotient F over E is supported away from L infinity. Okay, such objects have natural invariants, which are the rank of the sheaves involved, that I shall denote by R. Then we would have the so-called Chern classes, C1 and C2, but because of this triviality along L infinity, actually the first Chern class one can show that is forced to be zero. So the relevant invariants are just the second Chern classes of the two sheaves F and E involved. Or equivalently, we can instead substituting the second Chern class of E with this H0 of the quotient. And the relation is just that then we would recover the second Chern class of E as the sum of the second Chern class of F and this dimension of this cohomology, H0. Okay, so I will not explain the theory here, just believe me that it is possible with these fixed invariants to build a moduli space of such objects. Okay, that I will denote by F, R, and L. As always happens, to build a moduli space, we need to fix specific invariants, of course. In this case, rank, I recall again, and the second Chern classes of the two sheaves involved. Okay. The idea, I repeat, is to describe this moduli space as a moduli space of representations of a suitable quiver. This means that we would want to show that there is an isomorphism of schemes, in principle, between these F, R, and L, and another moduli space, I repeat, involving some suitable quiver that now I will introduce. The quiver that appears in the picture is the following, the so-called enhanced ADHM quiver, which is kind of complicated, so to speak. I mean, we have many loops, we have many closed paths here, and just three vertices that I will denote by 1, 1 prime, and infinity. This infinity is a special vertex. I will talk about this more later. And it corresponds to the fact that we have here this condition about the triviality along this, this line at infinity. So this vertex infinity will play a special role in the picture. Why this quiver is called enhanced ADHM quiver? Because if we just look at this part of the graph, we would recognize a very famous quiver, which was used by Nakajima in 1999 to describe precisely, so it's not random, frame sheaves on P2. Frame sheaves of P2 would be objects, simpler objects, where we have just F and phi, without the subsheaf E. Okay, and the name ADHM is just an acronym for Attila, Drinfeld, Hitchin, Manin, which were the first authors in literature that provided this kind of descriptions for the moduli spaces of bundles or sheaves in general. Okay, so we want to build an actual moduli space of representations for this specific quiver, the enhanced ADHM quiver. To do so, unfortunately, it is not enough to just consider isomorphism classes. Of course, the action of this product of general linear groups given by change of basis will be involved, but we cannot be so naive. So the way to build an actual moduli space involves a construction that was whose recipe was given by Alastair King in 1994, which is a kind of a GIT construction. Actually, he proved precisely that the recipe he was given in the paper was just a specific application of Mumford's geometric invariant theory. So we want to build, in principle, this moduli space. So we need to fix invariants for our quiver, and of course, as already explained before, the natural invariant for a quiver is a dimension vector. Here we have 3 vertices, and so we have to fix 3 dimensions, R, C, and C prime. In particular, R will denote the dimension of the vector space that we want to attach to the vertex at infinity. C, the dimension of the vector space that we want to attach to vertex 1, and C prime, the dimension of the vector space that we want to put here at vertex 1 prime. Okay, plus that's why I introduced this idea of quiver with relations before. We need also some relations. Why we would have to force the linear maps to satisfy this bunch of equations might not be clear in this talk, but it is actually kind of natural, because this first one is the so-called ADHM equation that arises basically by symplectic reduction. Let's say, okay, it is related to the existence of a moment map for the action of the group that we are considering, and it is precisely the equation that already appears in this paper by Nakajima in 1999. All the other relations that we have here instead, they just ensures that basically we can watch at this huge quiver as actually basically as a morphism of representations of this smaller quiver. Why? Because we can just add here another vertex, a dummy vertex, let's say like that, dummy vertex, with dimension 0. Okay, and then by adding now other arrows, this would not affect the picture, because by putting dimension 0, we are killing all the linear maps that would appear here. So that these commutations, like here with the map F, and this commutation here between the two linear maps A prime and B prime, just means that we can consider a representation of the enhanced ADHM quiver with that relations, I repeat, as a morphism between two copies of the same smaller quiver, this ADHM quiver, precisely as the geometrical objects are pairs of sheaves with an inclusion. So this reflects on the quiver side by interpreting this huge quiver, I repeat, as a pair of representations of the original quiver with a morphism between them. Okay, the main point in King's construction to build modular spaces, the more delicate one actually, is that we cannot simply consider all possible representations of a quiver. We wouldn't be able to build an actual modular space, but we need instead to select some nice representations, and to do so, we need to fix a so-called stability parameter that I'm denoting by theta, which is just a collection, in this case, of 3 real numbers, satisfying okay, a normalization condition, which is not that important, but I repeat, it's just a sort of normalization. In general, if our quiver Q would have n vertices, the stability parameter would be an element of R to the n. Perfect. Then we introduce a notion of theta semi-stability or theta stability. This is a sort of a slope stability that already appears in literature when considering the modular spaces of sheaves. And for quivers, we need first to define what is a sub-representation, which is just of a given representation, which is just a collection of subspaces of the 3 vector spaces that we are considering, of course, which are invariant, which means that these 3 subspaces are respected by all the linear maps involved. So we would have 3 vector spaces here, a representation, a fixed representation. A sub-representation would be a choice of 3 subspaces, such that the image to true F of the subspace here needs to be included in the subspace here. They have to be invariant under the action of all these endomorphisms and so forth. Okay, then we can say that a representation is theta semi-stable if basically these slopes is always non-positive or negative. When we have the strict inequality, we would get stability. When we allow also to have here the equality, we would get semi-stability. So this would be kind of a slope of a sub-representation. And this is, if you want, the slope of the representation X, because precisely of this normalization that we introduced before. This product would be precisely the inner product in R3. Okay, so it's a bit technical, but we need all of these to build a modular space. And of course, then we will need to mod out by the action of our group. In this case, the product of the general linear group at the vertices would be this one, GLV times GLV prime times GLW. But it is precisely here that the speciality of this framing vertex appears. So in parallel with the fact that we are fixing here and a specific isomorphism along this L infinity with the trivial bundle, Also, on the quiver side, we are fixing here a specific vector space without allowing the change of basis. So, in other words, the action of the group that we are considering is not this whole, but just the change of basis at vertex 1 and 1 prime. So, I have to erase this last factor. I repeat, this expresses precisely the fact that the framing vertex infinity is somehow special. Okay. Now, through a construction that I cannot show here, but which is very well explained in King's paper, we are now able to build then a moduli space of framed stable representations of our enhanced ADHM quiver. This moduli space, I want to stress it once more, depends on the choice of the stability parameter theta. So to be more precise, I should put here theta stable. Very well. So finally, we can state the first result of this couple of papers I am discussing today. This is probably the main theorem of the paper of 2017 by Rodrigo and Marcos. They precisely provided an isomorphism of schemes between the modular space of framed flags of sheaves with invariants R, M, and L, and a suitable modular space of theta stable representations of the enhanced ADHM quiver with dimensions R, N plus L, L. So there is, of course, a link between the invariants. If we choose the parameter theta in here, so this is the space, represents the space of stability parameters, which is just a plane because of the normalization. So we have an element of R3, but we are cutting with this plane. So we can solve, of course, and basically we have just two free stability parameters, theta and theta prime. So what they proved was that if we move inside this open cone, gamma, okay, so excluding the two open rays here, we would always get the same modular space, and this modular space is isomorphic, in fact, to the modular space of framed flags of sheaves that was the initial purpose of their work. A first improvement made in the recent paper in which I also collaborated was that we extended here the cone and we found out the maximal cone. So we sharpened the result and actually instead of this upper bound, we would get just the line theta prime equals minus theta here. And we proved that this is the maximal choice of the cone. And with the language of variation of stability parameters theories, we would say that this open cone is a chamber in the space of stability parameters. And we proved that here and here on the two open rays that I am indicating now, the stability condition actually changes. So there is no way to go to extend further this open cone without changing the modular space that we would get once we perform all the recipe given by King. Okay. Now let me just give some motivation about why this quiver is so interesting, or why we should consider these flags of frame sheaves. Actually, both these works involves some slight modifications of the enhanced ADHM quiver. In this first one, we would have basically an additional relation, which is A prime equals B prime, which means that we are gluing together these two loops. While in this second, very recent work, they are considering longer flags of sheaves. So if you want, this enhanced ADHM quiver is the building block, the simpler building block of the objects Bonelli, Fasola, and Tanzini are considering here. So motivations means that there are works in literature that are considering variations of this quiver. The truth is that both of this work involves some physical, like quantum mechanic, general nonsense that I don't understand. So my motivations are just that I know that it is interesting for physicists to use these results, these modular spaces. But unfortunately, I'm just able to mention just a couple of works, but I'm not able to explain precisely, for instance, what is a surface operator, or what are surface defects. I hope that it is enough for you. Okay. Are there any questions? Because now I would try to explain instead, which is the main content of the paper of 2021. Okay, I hope everything is fine. Okay. Okay, so I can continue. So let's just add one more thing, that in order to do the computations that they want to do in these two papers, it is needed some regularity of the modular space that we obtain. Okay. So in the ideal world, one would want smoothness. We would like to prove that all these modular spaces are smooth. This is unfortunately not true, but it is possible to prove something which is good enough for the purposes, I repeat, of all these applications. Which is that all the modular spaces we are considering have a perfect obstruction theory, which is just a first step towards smoothness. So it's a necessary condition to have smooth modular spaces, but it is not sufficient. What does this mean? It means that for every representation X, if we write down the deformation complex, which is a complex whose cohomology would basically try to describe the tangent space to the modular space at the point X. So I'm not very. It's not easy to explain how to build it. You can just look here of the differentials that we would get. That they're not at all simple. Let me just mention that the first map here would represent a linearization of the action of the group, while the second one, D1, would be a linearization of the relations. For instance, here you can recognize a sort of a linearization of the ADHM equation, while the third differential appears because there are relations among the relations. I mean that all these equations are not actually linearly independent. And so we would have this third map here. Then we can use this deformation complex through the usual deformation theory to compute the cohomologies of the complex. And this perfect abstraction theory means that we have these vanishings. Sorry, I didn't add 0 here. So that both H0 and H3 of all these complexes that depend, of course, on the specific representation X vanish. So that we would just have H1 and H2 that in principle can be interpreted as H2 is the so-called obstruction space, and the H1 would compute the Zariski tangent space to the moduli. If the dimension of the H1 would be constant by varying this point X into the moduli space, the moduli space would be smooth. But unfortunately, this is not the case in general. One thing that is completely good about this result is that, for instance, it allows one at least to compute the expected dimension of the moduli space, which turns out to be different if we are considering this invariant C prime, which I remember is the dimension of the vector space we attach here at 1 prime to be greater than 1 or precisely equals 1. In particular, we have 1 more in the expected dimension in this particular case that is in fact of some interest, as I will explain in a few moments. Okay, so this is the main result that I repeat we can understand as a partial result towards smoothness, or at least a result of regularity of the moduli space that the moduli spaces that we are considering. But of course, there are a bunch of open problems. The first one is precisely to prove actual smoothness. In general, there is no hope. For instance, by considering the spaces NR32, one can explicitly compute the cohomologies H1 and H2 through this huge complex, and one can explicitly find different representations that gives different values of the H1 that would represent the dimension of the vector space, of the tangent space. So in other words, the tangent space of this moduli space would jump. This means that these moduli spaces are indeed singular. So there is no hope in general. The case instead where this C prime equals 1, which is precisely the one with this anomaly about the expected dimension, is instead still open, and we actually conjectured that it should be indeed smooth. Why? Because if we consider the even more specific case of rank 1, one is able to interpret a flag of rank 1 torsion-free sheaves over P2 as a point in the nested Hilbert scheme of C2. Nested Hilbert schemes are objects that are very well known, and they were studied independently of this story that I told you. And for instance, it was proved by Shea in 1998 that all these nested Hilbert schemes, for all these nested Hilbert schemes, smoothness can be obtained precisely when C prime equals 1. So there is, in fact, hope that for higher rank we would continue to have smoothness. And in fact, there is no evidence that this is not true. More than that, we were able to prove a proposition that moves another small step in this direction. Okay, sorry. What I mean is that we were able to prove that at least inside NRC1, one can find a family of unobstructed points. Unobstructed points means points where also the H2 of the deformation complex vanishes. Okay. Okay, here you can see the explicit formulation of the points in the family, but maybe it's not that relevant. Actually, it is interesting that we proved that the set of unobstructed point is non-empty, because once we know that it is non-empty, so we actually explicitly found a family, but it would be enough to have one point to know that generically the modular space is unobstructed. This because it is an open condition. So the subset of unobstructed point is Zariski open inside our modular space. Another final open problem involves some other geometrical features of these modular spaces. For instance, it would be interesting to understand if they are connected or irreducible. The two things, of course, are closely related if we knew smoothness, but in general, there are two different problems. And why we may hope that our description through quivers could help in order to solve this problem. This is because we have natural morphisms, surjective morphisms from our modular spaces and the modular spaces studied by Nakajima in 1999, the ones involving just framed torsion-free sheaves on P2 and not flags of torsion-free sheaves. The map is very natural. We're taking the flag of sheaves and just forgetting the subsheaf E. And plus, these modular spaces are known to be both smooth and irreducible. So that one might wonder if by studying the fibers of this projection, maybe one would be able to connect all possible points of our modular spaces and prove, for instance, connectedness. Actually, this was stated to be true in the 2017 paper for C prime equals 1, so for a specific choice of invariants. But unfortunately, the proof there contained a flaw that we were not able to circumvent. So it is still open. Of course, we have also a quiver description here, so we can use the linear data here and the linear data here to try to describe this projection. So this is why, so to speak, our description can provide a powerful, in principle, tool in order to crack these open problems. Okay, so maybe I was a bit faster than expected, but this was everything that I wanted to say. So maybe I will stop here, and thank you.